Hi everyone, welcome and let us present the STS-MED project in Cyprus. STS-MED project, which stands for Small Scale Thermal Solar District Units for the Mediterranean Communities, has been supported with the financial assistance of the European Union under the ENPI CBC Mediterranean Sea Basin Program. This presentation will focus a bit more especially on the showcase at the Cyprus Institute in Nicosia. Cyprus is a small island located in the southeastern Mediterranean. Like in many countries in the region, summers are really hot and may last up to 6 months. Rains are rare, temperatures often reach more than 40 degrees Celsius in the afternoons. This leads to very high needs for air conditioning, which is responsible of huge electricity consumption in summer. Since Cyprus is an island with few fossil fuels, the country needs to import them to generate electricity. So reducing the needs for air conditioning relying on fossil fuels is a challenge which is undertaken with a pilot plant inside the STS-MED project. A huge effort also is dedicated to promote this solution to local companies in Cyprus. Due to its geographical location, Cyprus enjoys one of the highest solar radiation in the European countries. The horizontal irradiation is close to 2000 kilowatts hour per meter square per year in some areas and generally higher than 1850 kilowatts hour per meter square per year in the whole island. Horizontal irradiance is here expressed as the energy received on the flat horizontal surface for 1 year, and this surface is assumed to be 1 square meter. Similar values of such high irradiation can only be recorded in South Spain, Crete, South Sicily, as far as the European countries are concerned. On the top of the atmosphere, around 174 petawatts of solar power is sent by the sun. A part of it is reflected directly out of the atmosphere, around 9%. Another part is reflected out of the atmosphere by the clouds, 23%. 19% is absorbed by the clouds. So eventually, only 49% of the direct light of the sun is reaching the top of the ground. This remaining irradiation is called DNI, direct normal irradiance. 49% is an average on the Earth, but this varies from one country to another. Again, in Cyprus, the DNI is one of the highest in Europe and reaches almost 2000 kilowatts hour per meter square per year. This value is close to the value of the global horizontal irradiance as seen before. This demonstrates that few clouds are in the sky and few of them are in the sky mainly in summer. Direct normal irradiance here is expressed as the direct energy received on the flat surface of 1 square meter for 1 year tracking the sun. The energy from reflection or diffusion by the environment are not taken into account. A pilot plant was built in 2015 at the Cyprus Institute in the outskirts of Nicosia. The purpose of such a pilot plant was to provide air conditioning to a near to zero energy building called Novel Technologies Laboratory, NTL. The air conditioning system has been upgraded with the installation of a Fresnel collector, as we can see on the bottom left. Fresnel collectors concentrate the sunlight according to a single axis tracking method. It means that rectangular mirrors or several mirrors in series are driven by one motor only, following the longitudinal axis. The mirrors are slightly curved in order to concentrate the reflected beams on the receiver. Usually, reflection of the mirrors is higher than 92%. The receiver is located some meters above the mirrors in the center of the field, and it's aligned with the rotation of the mirrors, which is usually in the northern countries like Cyprus, aligned according to the north-south meridian. All the reflected beams are also concentrated inside the receiver. The heat is then transferred to a fluid in circulation. The weight of such collector is quite low, around 25 kilograms per square meter. The wind load is low due to the low height of the field, so Fresnel technology is one of the only technologies able to be fixed on a roof. Sometimes the installation of such system requires preparation of the field or the roof with fixing and beams. The Fresnel collector at the Cyprus Institute is located on the roof of the Kepa School, which is separated by a road from the Novel Technology Laboratory. So on the top right pictures, we can see on the background the NTL building, and in the foreground the Fresnel collector. Both of them are separated by a road. The reflective field is composed by 288 mirrors. Each mirror is 2 meters long and 32 centimeters wide. 16 mirrors are aligned per row, and the rotation is ensured by 4 DC motors. The field has an aperture area of 184 square meters. The pilot plants at the Cyprus Institute relies so on 8 modules in series. 72 DC motors drive all the mirrors and 4 per each row. The 32 meters long receiver encloses a secondary receiver which concentrates twice the spare beams from the mirrors around the pipe. The receiver encloses also a vacuum pipe through which circulates thermal oil reaching 180 degrees at the outlet. The heat produced fires an absorption chiller which provides cooling to the building thanks to heat. The absorption chiller installed for the NTL is a lithium bromide chiller with a cooling capacity of 35 kilowatts, and its coefficient of performance is 0.7. An absorption chiller like the one installed at the Cyprus Institute has 4 chambers. First, the absorber. The refrigerant vapor, means from water, leaving the evaporator, is condensated and then absorbed by the written lithium bromide solution from the generator into the vacuum of the absorber. Heat of the dilution and condensation is removed by the cooling fluid from the cooling tower. The generator, the solution is heated by the heat produced by the Fresnel collector, and then the refrigerant water evaporates. The liquid lithium bromide is expanded back to the absorber, condensed and mixed with the refrigerant. Cycle is then the same as a classical refrigeration in the condenser and the evaporator. We can see here 3 different loops. First, the chilled water. The chilled water is the liquid from which heat has to be removed. So usually the inlet is 12 degrees and the outlet 7 degrees for the Cyprus Institute. It's the liquid which is providing cooling to the building. The cooling tower system permits to condensate the refrigerant to remove the heat from the chilled water. The heat input permits to replace the compression effect on a classical vapor compression refrigeration. Heat input is required, so it can be solar energy, fossil fuels. In our case, it's solar energy, and this can reduce dramatically the use of electricity, like for mechanical chillers or classical heat pumps. The HVAC system of the Novel Technologies Laboratory was implemented before the installation of the Fresnel. Indeed, the NTL is in use since 2013, and the Fresnel collector was installed in 2015. So the solar cooling system is integrated to reduce the use of power elements such as 2 mechanical chillers and 1 heat pump. All these components provide cooling to the building, consuming huge amounts of electricity. Cooling and heating is then sent to the rooms with the help of numerous air handling units and fine coil units. Many other components such as circulators, stratified tanks, heat recovery units were previously installed in the HVAC system. So the challenge here is to implement the solar cooling system on this heating, ventilation, and air conditioning system. The Novel Technology Laboratory is a three-story building and has one basement. 26 permanent persons occupies this building, which is dedicated to research activities and some administration. The thermal needs of the building is typical from the industrial buildings in Cyprus. High needs for cooling in summer, lower needs for heating in winter, and also HVAC is only solicited during office working hours. So during the weekends, HVAC needs are really limited or non-existent. The Fresnel collector was integrated to support the HVAC system. The thermal oil used exchanges its heat with a loop of pressurized water at 140 degrees. This configuration permits to store the heat up to 2 hours, so the heat produced can be released later for later use. In other words, when the storage is full, the absorption chiller can be autonomous for 2 hours in case of clouds. This is the main advantage of concentrating technologies such as Fresnel. The temperatures can go to higher temperatures than for conventional solar thermal collectors. This permits so to store at higher temperature and to shift the production even during the night by the creation of a higher temperature difference between the thermal storage and the temperature required by the system. For instance, at the Cyprus Institute, the heat is stored at 140 degrees and the absorption chiller requires only 88 degrees. The size of thermal storage reduces as a consequence. Also, thanks to the use of high temperature, double effect or triple effect chillers with higher COP, higher than 1, can be used. The heat is then transferred to heat medium loop for the absorption chiller. This way cooling is provided in summer. In winter, the absorption chiller is bypassed and the heat is released for heating. Eventually, the electric power elements such as heat pumps and chillers are less solicited, and this leads to reduced electricity consumption. In 2014, 71% of the electricity consumption of the building was due to the heat pump and the mechanical chillers. In other words, this amount represents the needs for air conditioning. The electricity used for the laboratory activities is not included in this energy balance. On the roof of the Novel Technologies Laboratory, a photovoltaic generator of 15 kilowatts peak power was installed and contributed to compensate up to 20% of the electricity consumption. So, by reducing the use of the heat pump and the chillers for the air conditioning, we reduce indirectly their electric consumption. The objective of the installation of the Fresnel collector is to reverse the proportions of 20-80% between compensated and non-compensated energies, and to have a new proportion of 80-20. So basically, to almost cover all the needs of the building. As a conclusion, using solar concentration can contribute to reduce the electricity consumption in countries using huge amount of electricity for air conditioning like in Cyprus. So this solar concentration can provide cooling in summer and heating in winter. Fresnel collectors are a unique kind of collectors able to be integrated on buildings as well. Thermal storage is the key of such systems, which enable to store the energy at higher temperature and to shift the production even for the night or in cloudy conditions. Absorption chillers are interesting devices using the heat to produce cooling So this is also relevant for countries like Cyprus. But all these technologies still need to be further developed in order to demonstrate their techno-economic feasibilities. Thanks a lot for attending this presentation. This is almost the end, but to finish, this presentation will be followed by a time lapse. This time lapse is a time lapse of 2 weeks of installation of the Fresnel collector, which was mentioned in this presentation. Don't hesitate to be in contact with me using the email you see on the right bottom of the slide. Hope you enjoy it. Cheers, Alaric.